Hi, good morning all. We're here this morning to look at RGB and DC basics. My name is Pete Peters, as you can see in the bottom down here, and that's my email address right here. So if any of you have questions about any of this information later on, I'll be happy to field any kind of questions that you may have. And there's my email for you once again. So it's p_peters69@hotmail.com. RGB is the big and up and coming, and already is as far as that goes. I've given you a couple examples here which we'll look at a little bit later in more detail as to what these are. So if you haven't really seen them, you're kind of going to get a drift on that, and Dennis will probably follow up with even more on that. The DC basics is what I'm going to really be pushing on as far as that goes, as far as the topic goes. What we're going to look at now, we need to have a little background information relating to what AC and DC is. Well, AC, first of all, is alternating current. It's not the same thing as voltage, by the way. We're talking about current here, which is amperage. So alternating current, and essentially when you think of alternating current, think of it in terms of pulsing or going on and off. It's not there all the time. It's got a specific on and off sequence based on the frequency. And ours in this country is 60 hertz. If you're in someplace else, it could be 50, etc. But again, it has to do with the timing of the on and the off sequence. AC, again, is used throughout the U.S. Primarily, we are the biggest users of alternating current. It's available in voltages from 120 volts up to as high as 600 volts. Typically, you can find it higher, but these are the normal levels. You can also find it lower as well. AC, however, for us to utilize it in our electronic circuits, we've got to convert it to DC. So let's take a look at what the DC conversion actually is. DC, obviously, as I said before, is direct current, meaning it's steady, always on. It does not change, does not go on and off, doesn't change in its operation. DC is usually used by almost all forms of electronic devices that we have. Now, especially for our LEDs and RGBs, I'm calling RGBs pixels because that's kind of the term out there for it. It's also reminiscent of the old days of color television when they were talking about the screens. Pixels were what they talked about with the little illuminations that they were looking at. Chips, ICs, integrated circuits, and virtually anything that's electronic. DC is usually used with the voltages. Now you'll notice I'm saying direct current, and I'm making a difference here between voltage because you'll see the term VDC. They're talking about volts and direct current together, or volts AC, VAC, okay? But there's two separate things going on there. Typically we're going to look here at the 5 and the 12 volt versions, and that's what our RGBs, pixels, and chips primarily work at. You'll also find that there's some other common ones in here at the 24 volt level and the 3 volt. They're not as common for what we typically do, but those are still nonetheless available for us as far as these particular things go, for our LEDs and RGBs. Without any further ado, as far as the background goes, we need to understand when we're looking at RGBs or any electronic component that we need to deal with watts. And the watts is what we basically are going to call power. Power is the availability of our circuit to do work. And the way we get that is by combining a voltage and our amps together. If you look at the voltage, what it basically is, if you think of it in terms, it's a pressure that pushes the electrons through the circuit. The combination of both of these, as you can see, will give us watts. Okay? This little chart that I've got over to the side, if you're going to try to find values, and for us, watts and amps are primarily going to be the ones we're looking for, you'll notice that the V is for voltage. The I here is related for amps, and you may wonder why we didn't change it to A, because typically what you're going to see in most of your calculations is the letter I, which stands for intensity. It's still the same thing in amps. If you look at it for A, no big deal. Power in watts, and again, when we talk about power, when somebody says, give me power, what they're talking about is not voltage. They're talking about these two elements in combination together to give us watts. The ability to do work right here. So if we want to find something out, we have an ability now by using these formulas down here, which is called Watt's Law, and we're using our little pie chart up here. Very simple. If you're trying to find power, for instance, which is watts, you would simply cover the P with your hand or whatever, and you would multiply V times I, your volts times your amps, to get your power. If you've got, and you know, for instance, you know where your power is, and you know what your current levels are, you can find voltage. That's the V. And what you do is you cover the V. P divided by I, or A, amps, gives us volts. And the same thing for the current levels. Again, current, I, or A, if you want to call it that. Cover the I, and again, it's power divided by volts. So with this in our little arsenal, we essentially can figure out pretty much what we're going to need to provide for our circuits based on our level of work, power, based on our level of voltage that we're going to be using, and then that will affect the ampacity that we're going to be required as well. Here's a couple examples of the use of Watt's law for us. Real simple, a 100-watt power supply. Now remember, power supply. Okay, so what we're doing here is we're providing power. We're not providing voltage as much as we are providing power. So power supply needs a 12 volts DC to operate. How many amps will the power supply require? Well, using our Watt's law, real simply, we could figure it out. It'd be 8.3 amps. Again, watts divided by volts. So again, using our chart, if I'm trying to find amps, cover my I, power divided by volts gives me my amps. Next example is a 50. We're using 50 RGBs now, LEDs. They operate at 12 volts DC, and they use approximately 0.25 amps. Now I'm going to stop a little bit right here. You'll notice on the side of it I put 250 small MA. That small m refers to milli, which means 1,000. So what you're going to see a lot of times with your power supplies, especially if they're smaller, is you're going to see them rated in milliamps. That's 1,000th of an amp. So to get back to amps, you must divide that number by 1,000 to get us back to amps, because our formula will not work with the milliamps in it. You have to use full amps or the full base unit for that particular thing. So you'll notice I've also put I over there. That's just to basically identify it with our chart so that you can understand that's the amps. Most of the time you'll probably see it with either A or MA on the listing. Okay, so how many watts will the power supply need to supply? How many watts will it actually supply? Well, again, if we're looking for watts, we know that that's going to be a combination, or basically using volts times amps to get us the power. 3 watts would be the thing, or you also might see it listed as 3,000 milliwatts, or MWs. So this is not an uncommon way to see it. A lot of engineers like to have this particular thing out because they basically, their circuits are based in milliwatts, millivolts, milliamps, etc. But you can get the drift of what's going on. Again, 12 volts DC, direct current, times 0.25 amps, 250 milliamps, gives us 3 watts or 3,000 milliwatts. And again, you can see the relationship, milli 1,000, right? So 3,003. The label on your power supply is damaged, and this is a common occurrence. Things happen to our power supply labels. You can only read the watts, so you know it's 100 watts. And basically you see the amps. Maybe it's 8A, or maybe it says I on there, or maybe it will say something a little different. Maybe it'll have a combination. But nonetheless, 100 watts, and we have 8 amps. So we know if we've got watts and we've got amps, but we don't know what the voltage is. Using our formula again, are we going to cover up V? That means that we would divide our power by our current, our I, to get the voltage. And as you can see right here, that 100 watts divided by 8 amps would give us 12.5 volts DC. So using this, we can more or less figure out almost any given problem, any given requirement for our circuits with our DC. This also works with AC, but we're concentrating now on DC. Okay. All of this is stemming down to one thing basically, and that's to power up our newer technologies, which isn't so new anymore, really. This, what we're looking at right here, is actually what I'm going to call a pixel. Nothing more than an LED. As you can see, the LED, I'm pointing here. You'll also notice that I'm making a designation here of chip on this. That chip, that little black square thing there, that's an integrated circuit, and essentially that's what makes this guy, this pixel, smart. What do I mean by smart? That means that that one pixel by itself can change up to 6 million colors by itself. That means all the rest of the devices, all the rest of the pixels in that particular string can do the same. If that chip is missing, that means that whole string then would be one color. So if this was blue, all the rest of them would be blue. But this way right here, we have the ability, yep.
Pete?
Yep.
Would that be referred to as a dumb string?
That's a dumb string. Yes, it is. Dumb string, exactly right. So dumb and smart strings are pretty much what we're going to be, we're not going to be looking at the dumb ones, we're going to be talking about smart ones here. But anyway, the point being the chip, this little guy right here, that makes the difference as far as what we're looking at. And this also requires more channels for us to use in our system as well. The specification sheet is important to us when we're utilizing RGB or pixels, because we need to understand how much each one of those little boards that we're going to be powering needs. And that's what this is called. This is right here. You'll notice it says power consumption. Power consumption. So what are we talking about again? We're talking about the relationship between current and voltage again. In this particular case right here, I've marked it as saying watts, because that's what we're looking at. And this tells us 0.3 watts, and that slash means per. It's a division sign, per piece, PC. So that means each pixel. In that particular diagram we looked at before, there was 50 pixels. So now I have 50 of these that require 0.3 watts each. So my power supply, or my source, has to be able to give me the entire amount of watts that I need, which would be 50, basically, times my 0.3, which would give me a total of 15 watts for that entire string. That means that my power supply would need to supply for each string 15 watts. And remember, watts is power. Okay, so watts and power, keeping those in mind, are the same thing. And you'll notice they've already given us what the voltage level is. All right, they've already given us that. We don't really need that at this point because we've been given the watts, and the watts is what we're looking for. This is another version, what we call a square pixel. These are 50/50s. Also, it has to do with construction. But again, the big thing I want to make you aware of is that little IC right there. This is the bottom of this particular square, and that's the chip. That's the integrated circuit. That's what makes this thing smart. Without that in there, again, you're going to see that all these LEDs would be turning on at the same time, at the same color, which is at the same frequency or the same signal. So you can see the bottom of the LED, and as compared to what the top of the LED would look like. Again, smart RGB. And RGB, by the way, I'm sure you all understand, but that means red, green, and blue. Those are the primary colors. If you mix those all together in different ratios, you will form all the colors, if you will, of the rainbow, including white, which means that we simply have the same virtual amount of our red, green, and blue all on at the same period of time. This is the specification sheet now for the square, that little 50/50 that we looked at up there. And you'll notice that it's fairly close to what we looked at before. This power consumption, this is what we're always looking at, and they spell it out for us right here. Power consumption per piece. So this is at 0.24 watts. And again, they've given us the voltage at 12 volts, but they put the DC on the other side this time. They're just telling us that it's direct current and it's driven or pushed by 12 volts. So for that string, what we see there, again, we've got 20 of those 50/50s that are in there, the squares. They require 0.24 watts, so times that, times the 2.24, 4.8 watts. Now if I was going to utilize both of those strings together, I would be adding this amount to the previous amount, because watts is all we're really concerned about with, because our power supplies are going to need to deliver us watts. So if we deliver these guys, when we add these up, we will have the total number of watts that we need for our load. And that's what we're looking at here, the load. The load is what we're attaching to our power supply. So that's our lights. That could be, it could be a radio. It could be almost anything that's electronic that requires that voltage level. Anything that requires the voltage and the current together to provide work, power, that's what we would do. We simply would add it up. So if I had 4.8 and we had what the value was in the other one, that would be how much power I would need my power supply to be able to put out minimally at that particular voltage, which is 12 volts DC. Okay. Okay, once again, this is a little slide in here. I'm blurping this again. That's my email. And again, please, if you have any questions on this stuff at all, because I'm hitting this stuff pretty quickly. If you have any questions, please email me. I'll be happy to give you any information I can, any help I can. So we're going to look a little bit at how to size our power supply. And this again, you'll notice is very similar in what we were looking at before. Usable watts, however, this time. Now remember, we're sizing our power supply. This is what we're going to be looking to do. And to find our total wattage, okay, of the power supply, you multiply volts times amps. Well, that's just what we did. Just before, power supply has to provide the amount of power that we need to drive our circuit. Now you'll notice what I said. Here's the total watts. So that would have been a combination of both of those strings, if we were looking at those strings before, times 0.8. That means it's 80%, basically, of that total. It's what our power supply value, not of what our load is, but what our power supply would be able to provide comfortably. And what I mean by comfortably is this usable watts takes into effect the heating effect of our current going through our power supply. We do not want to overcurrent or overpower, if you will, or overheat our power supply, because we will shorten the life. So what we want to do with this is we want to only use 80% of that supply. Here's an example. 12 volt DC, 4 amp power supply has a total of 48 watts. Okay, how do we hit that? Remember, volts times amps, total of 48 watts is our output. Our usable watts for that particular amount of output would be 0.8 times basically our 48 watts, which would give us 38.4 usable watts. Now that's not to say that those other watts aren't still there. They are. And yes, you could run your system up higher on that. You could run it to the full load. You could run it to the full wattage of that power supply. But what you're going to do is you're going to decrease the life expectancy of that power supply. This also, as we're going to see in a little bit, will also allow us to take into consideration ambient conditions and other things that will affect our circuit, such as cable runs that are sitting out to our loads from our controllers, for instance.
So Pete,
Yes.
question?
Yep.
So you mentioned that you've got a total usable watts of your power supply. Essentially, you mentioned that if you run it at the full 48 watts, which is what the power supply is rated at, then what happens is you would shorten the life of your power supply. But is there what would additionally happen if you were like overdriving, if you were going over those 48 watts? Is that something where you're going to start triggering the overload circuit inside the power supplies? What happens at that point?
What would happen on that in most of your better power supplies essentially would look, this is a power supply right here, by the way. And this is an old Archer 12 volt power supply. And what I'm going to do is I'm actually going to open this guy up for us so we can kind of look inside. So we can get the idea behind what we're looking at. Essentially what you have is a transformer in here that's taking the line voltage, for us would be normally 120 volts. And the secondary side, which is this other side right here that connects to the output terminals back here, gives us in this particular case, if you look here, you can see that there's 13.5 volts here at about 1.75 amps. Now, if I were to take this guy here, it tells me right here, that's my output. I do not want to exceed that value. If I exceed that value, you'll notice right here, there's a little thing that says reset. I don't know if you're able to see this, but this is a little circuit breaker. This is set at this particular ampacity. So that basically means that if I have 1.75 amps here, or I go over that, this circuit breaker will open up and stop my circuit so that I cannot overdrive this guy. If you don't have that in there, you would then continue to have your output still drawing, and what would happen is the level of heat that would be developed here, because as we develop more current, which we would start developing more current, would start to overheat all the components inside the actual power supply. And therefore, eventually it would get so hot that the stuff inside here, the actual windings and so on, would actually short out. So you would burn up the power supply, in other words. It wouldn't catch fire necessarily, but you most assuredly would shorten its life by far or completely destroy the transformer.
Let the magic smoke out.
Yes, let the blue
Let the
smoke
smoke
out. You don't want to do that. Yeah, exactly. So the thing also too, when we're looking at power supplies, and as Mark was asking here, you'll notice on this guy right here, you'll see a couple of values listed. And this could confuse you when you're looking at power supplies. Because you're going to start looking at our Watt's law, and you're going to go, hey, watts is volts times amps, right? Or if I want to go ahead and find out what my ampacity is, I can divide my watts by my volts. Well, let's take a look. They've given me two values here. You probably can't see this, but on here it gives me the line side, which is your primary side of your transformer. On that, it's 120 volts. But you'll notice on here, you probably can't see it, it says 40 watts. Well, if you do some math on that, that gives me about 0.3 amps. Okay? That's really not a big problem for us. Now, if I go ahead and look at this one and take 13.8 volts DC, and I've got an output rate of 1.75 amps, if I do the math, it will give me around 24 watts for output. But didn't I just say this thing had a rating on the primary of 40 watts? Yep. The reason that that's there is that's not the continuous rating. That is not the continuous rating. And be very careful when you're buying pre-made power supplies, because they will give you many times what they call the initial or startup current or startup value, watts in this case. The actual one that we're going to be able to run this at continuously is this 1.75 or that 24 watt value. 40 watt rated at startup, but 24 amps continuous. Why do we need more? Because there is a surge. In all electrical circuits we have a surge when we are starting or applying our power initially. So we actually develop more current at that particular moment in time. And so this particular device, this power supply, it has been engineered so that it will take up to that 40 amps without tripping out the breaker, without doing damage inside here, but to continuously run, it's only going to be pulling 1.75 amps at 13.8 volts, which is 24 watts continuous. So when you're looking at power supplies, look at the continuous side, which is your secondary side, which is the output side when you're doing this. Otherwise, if you were thinking, I've got 40 watts available, and you go ahead and you hook up your lights out there, your RGBs, and they're at 36 watts, all of a sudden this thing begins to trip. Why? Because you've exceeded the continuous rating. It's going to only last that way for a very short period of time, maybe less than 2 or 3 seconds, and then it will trip. So always look at the continuous or output rating and use that value. So use the voltage and the current if you got that, or the watts on the output side. Okay? So that's our little, if you will, anatomy of our power supply. Transformer. Basically inside here we have something called a rectifier, which is what we call a bridge rectifier. You probably can't see it. It looks like a little square block, but there's 4 diodes in there that are 180 degrees basically apart. And what it's doing, remember I said AC has to be converted to DC? What it's doing, and remember the AC is turning off and on, 60 times per second. Yeah, here. So on and off, on and off, on and off. What that virtually would do would create pulses for us. And remember, DC, direct current, does not pulse. It needs to continue in a steady state. So what these diodes do is they limit the direction that the current can flow. And because we've got them flipped in there at 180 degrees apart, when one side virtually is on, the other side is off. So our cycle, if you will, our cycle, one's on, one's off, one's on, one's off, one's on, one's off. Because we have 2 sides to each cycle. We have a positive side, if you will, and another side, which we call the negative side. It's not really that way. What actually happens in that case is we have a direction of current flowing this way, and then when we go to the other side, when it turns on to the other side, it goes the opposite way. So you have flow this way, then flow this way. So if we put our diodes 180 degrees apart, we only allow flow to go through on this side, but normally if we didn't have this other diode, we would not have this side of our cycle. So by putting our diode in that direction, we then are able to get this flow. So that gives us what we call full wave rectification. Another thing too, you probably want to do when you're looking for your power supplies is make sure you have a full wave rectified supply and not a half wave. If you have half waves, you'll find out that your LEDs will be turning off and on at a very rapid rate. Some people can't see it, but some people can. That's what gives you the little flicker effect. So we definitely want to make sure we have a full wave here. We also, because that gives us not only the ability to not have that flicker, it also gives us the ability to use both sides of our cycle. Just a little recap on our sizing of our power supply. Basically, to determine the load you'll need. Okay, well, that's going to be, the load, remember, is going to be our lights, what we're putting on the circuit. Okay, so that would be your RGBs, that could be your spots, that could be a yoke in the yard, it could be a lot of different things. We know how to find it. Basically, you're going to find the voltage and the amperage of the load, and basically you're find the total wattage. If it's given to you, if you know wattage, for instance, if you had an MR16 lamp, for instance, an LED, they typically give you a voltage rating and the wattage on there already. We're concerned with wattage because that's what we are looking at to produce the work. Watts, power, does the work. So if we know what the wattage is of each one, of our loads, our lights, whatever we're applying, all we have to do is add them up to get us the amount of watts we need. Okay? We don't have to do any of the volts and the amps together if we know what the watts already are. If we don't have watts, and we have voltage and amps, then we do need to go ahead and perform Ohm's law or Watt's law on that to get us to those watts. Okay, Watt's law, we know what that guy is. We've got the little circular pie chart in there, easy to use. Remember, whatever one you're trying to find, whether it's watts, whether it's current, or whether it's voltage, simply put your hand or cover that one that you're looking for and perform the function. If it's above and below one another, it's a division. If they're side by side, it's multiplication. Okay, so I've got down here, remember I said we were only going to use 80% of our power supply because we want to keep it running cool. We want to keep it with a usable life that's not going to be impeded by the current levels. So what are we going to do to compensate for that? Because you're thinking, well, I'm losing all that power. You're not losing it. What you're doing is you're allowing the system to compensate for other conditions so that heat doesn't develop. I'm saying to go ahead and take the wattage that you need, your total wattage, the amount you need, multiply that by 1.2. What am I doing? I'm now taking 100%, but I'm now adding another 20% to that. So what that's going to do is it's going to increase or basically expand our usability by 20%, therefore letting us use 100% of our load value and still leave us with 20% over, if you will, to compensate for other problems. Now that's where I'm going down here. Remember, 80%, right? 80% is of the total wattage for our supply, not of the actual load, but for the supply. All right? And that's why we're going to multiply it by 1.2. So whenever you've got it, if you say, for instance, you needed 100 watts total power, all right, you'd multiply it by 1.2, so your supply, your power supply would need to be 120 watts. So that way you've got the full load that you can put on there, and your supply is still going to be able to compensate for any conditions. And even if you wanted to add a few things to it, you could to a very minimal level. You could take it all the way up if you wanted to, like I said, to the 100%. But what are you going to do? You're going to shorten the life of your supply doing that. Here's a little example, just to reiterate on this. It says you want to power 80 MR16s. An MR16, if you don't know what that is, basically is a round LED with several LEDs in it, if you will. Each LED is labeled at 12 volts DC at 1.5 watts. So essentially what that's going to tell us is that the MR16 needs 12 volts to operate, and it's going to use 1.5 watts each. We're going to take what? We've got 80 of them. 80 of those times that 1.5. We don't have to do anything with the voltage at this point. 1.5 watts basically is going to give us 120 watts. That's my total. So I am now going to multiply that by 1.2, and that would give me 144 watts total that I need for my power supply, to supply. So you'll need a power supply that delivers 12 volts DC with 144 watts. Now, if I wanted to figure out what my amps were, All I need to do is divide my watts by my volts, and in this particular case, that's going to work out at 12 amps. Okay. It's important for us to understand this ratio of amps and volts and watts, because we're going to need to do something like hook things up. We've got to get from our power supply next to our load, and that's the next section we'll be taking a look at. Voltage drop. Now this is going to probably be a little confusing to some of you, but I'm going to try to make it as simple as I can. I think you'll see that it's not going to be as hard as it looks here, because there's a hell of a lot of formulas here, excuse me. But nonetheless, we're only going to use two of these. And of ones I've got marked, and the one that we're going to start out with is wire size. So if I want to find my wire size, now remember what I'm doing now? I'm connecting my power supply now to my load. Okay, this is what I'm doing now. The wire size here, we figure it by an electrical term called circular mils. It's a cross-sectional area of wire, of the actual diameter of the wire, the actual, excuse me, not the diameter, but the actual surface, the square inches of the actual wire itself, measured in 1 foot at 1 mil, which is 1/1000th of an inch. So the formula we're going to use here to help us find out what wire size we need is we're going to use this information. Now the circular mils, you'll notice there's a chart over here that has cm in it, circular mils, and you'll notice that the American wire gauge is right here. We won't use this diameter mils or the other areas. If you wanted to use millimeters, you would use the area at millimeters squared, but we're not going there. We're going to use circular mils, and we're going to use the American wire gauge, which is what we size, if you will, our wire with. You'll notice that I have to point this out to you. I've got another one down here, 18AW, which stands for American Wire Gauge. And the circular mils for that is 1620. Well, if you notice in the chart I had, there's a little snafu. 18 and actually 19 are missing, but since we're not using 19 very often, 19 gauge wire is hardly ever used. The 18 gauge is very much more common for us to use. So I included this in this chart so you'd be able to utilize our formula as we're going to see. All right, let's look down here. The colored arrow here is the voltage drop per minute. VD is about voltage drop. Now 3% is what the National Electric Code, and that's where this table is based from, the National Electric Code, says that we do not want to have more than a 3% decrease of the voltage that we are using. In this particular case, I used the example 12 volts DC. And I've taken it times 0.03, which is 3%. That would equal 0.36 volts. So what does that mean? I would take that 0.36 volts away from 12 volts to give me the value of the maximum amount of voltage I could have underneath the 12 volts. Voltage drop. Okay. I don't really want to do this. I don't want to get anything more than that, because if I start dropping my voltage, remember there's a ratio here, right? Because to get watts, we have to have what? Volts and current together. And they are in direct proportion to one another. Because remember what? P is equal to our volts times our current. So if I change one of the volts, or I change the current, it's going to do what? It's going to affect my watts. I don't want to affect my watts. My watts wants to remain the same. Why? Because that's what my load is. That's what I need to power my load with. So if my voltage drops, what has to happen? My amps have to increase. My amps have to increase. Well, what does that do to my circuit? That puts more current through there, which brings more heat involved, and thereby problems for my circuit. So I don't want my voltage to vary. Voltage wants to remain fairly constant throughout all of our circuits. We don't want to really have a change. So the 3% is what we're going to use as our rule of thumb there. Cm, which is circular mils, indicates the size of the conductor. And if you'll notice, it says table 8. Table 8. This is the table we're using. There's other tables available that you could find, but for right now, this one here is the one we're going to use, and it's actually based on the National Electric Code. The green arrow is going to indicate the distance of the circuit one way. So what am I saying? I've got my power supply sitting here, and I've got my lights over at 25 feet away. That's what I'm talking about between here and there. That's my distance. That's 25 feet. So that's the number I'd be using here. Distance one way. We look at a circuit in coming to it and coming back from it normally, when we're figuring out total resistance and all that, but we're not going to mess with that. We're going to simply look at the one-way direction. The other thing we're going to be using here is something called the K factor, and this is a constant. This is a constant, and it's based on the material, as far as what the atomic ratio, if you will, atomic weight ratio is. For copper, it's 12.9. That's an approximation, it's not an exact. If we were going to actually try to figure out the exact one, we could actually go to another table, which even gets more confusing. So for us, we're going to use this one, and primarily we're going to use copper. We're not going to use aluminum. I really highly recommend you do not use any aluminum in your shows, any place outside, because aluminum corrodes, it's brittle, it will break, and you'll have nothing but problems with it. So copper only. So whenever we see K, we're going to be using 12.9. Now, so let's take a look at what this means. Here this is the blue arrow. The blue arrow down there indicates circular mills. And what we're trying to find, wire size here, is going to be circular mills. If you'll look at the chart, circular mills, certain amount of circular mills. Let's look, for instance, at the actual, let's look at number 20. What we see here is we have 1,022 circular mills, and that's going to give me a wire size, an AWG wire size of 20. Okay, so we want to get our circular mills so we can figure out what the actual American wire gauge size is we're going to use. Standard building wire we typically find is usually in number 12, number 14, 16. We primarily will be using 18, 20, 22, and probably 24 gauge. And you can see that these guys are listed on here for us. The 22 and 24 gauge are probably going to be used in terms of using category 5 or category 6 cables, because that is the actual size that we typically find in those cables. We can do the same thing. This formula works for every kind of wire that we have. Okay, we can find out the size. The reason this is going to be important is because we're going to be, look at this, what they're asking here, the VD here is what our volt drop permitted. So what we're going to be doing is we're going to be taking the voltage that we want to use in our circuit, we're going to be taking that times 0.03 here in this particular case, and then we're going to divide it into 2 times the actual K factor, which would be 12.9, the distance in this particular case, whatever that was, if it was 25 feet, and the current that we want our circuit to operate at. So if we're going with those particular elements, we basically would multiply those together, divide it by the voltage drop permitted. In this particular case, all you have to remember about VD is that it's going to be 3% of whatever voltage level, whether it's 12 or whether it's 5 volts, doesn't really matter. Still the same thing. And the reason we want this is so we can size our wire for that voltage drop. Now keep in mind one thing. What we're doing here by sizing our wire is we're keeping our wire cool. Just like we were using 80% of our power supply, we're now going to size our wire so that it is cool as well. Just by making something larger is not going to affect my voltage. There's a misconception out there that, if I don't have enough voltage at that far end, all I need to do is upsize my wire, get a larger size wire. And by the way the American wire gauge works is that the larger the number, the smaller the size of the wire. So you see way up here, this is 4/0. That is huge wire. That's about that big around. If you're looking at number 20, it would be about the size of that wire right there. So you can get kind of a comparison between the two. So remember, the larger the American wire gauge number, the smaller the wire. All right, so if we're looking at what we're trying to figure out on this particular case here, is we don't want to get the misconception that just because I've now figured out my wire size and I've taken into consideration my voltage drop, that everything's fine. Not necessarily. Your voltage is not going to change. Your voltage does not change. What it's going to do is it's probably going to get less as it goes further along. Why? Because we have things called resistance in our wire. This is trying to size the wire so that it will take more amps. Remember, because if we're changing our voltage at that far end, what are we doing? We still have to have the same amount of power available. So what has to happen? Our amps have to come up. So as a result, we need larger wire to carry that greater amps and to keep our wire cool.
Pete?
Yep.
So we're kind of restricted with what we can do, because the pixels that we're buying from China or wherever have a fixed wire harness that we have no control over. So basically, we will have 42, 50, 85 nodes on a string, and we will have a fixed diameter. So in reality, the only thing that we have available to us to calculate or to affect is distance from power supply to pixel string. Correct, right?
Yep.
So it, you know, in the fact that we understand how long the pixel strings are, that there's a diameter gauge wire that's obviously the wire harness between that. What's the relationship or the ratio of those types of elements in terms of the length of the wire versus what it's going to take to drive that, the size of the wire to drive it for a certain distance? Is that kind of...
That's what we're kind of doing, Mark. What we're doing is we're actually getting the power to that string. Now, as you mentioned, the string comes from the factory already figured at a specific wire size. Now, that wire size that they have on there is calculated by their engineering staff, if you will, based on the voltage that's going to be in that string and the actual resistance of that string. So they have sized it, if they've done their homework right, they have sized that wire that's there that will handle that ampacity for that string. So we don't have to worry with that. What our worry is getting from our power supply to the string and providing the proper amount of voltage and power.
At the beginning of the string.
At the beginning of the string. Exactly right. We don't care about what it does throughout, because
Well, we do.
Well,
we do, because we could, at some point, if the string was long enough and it was required, we could re-inject power at the end.
yes, you could. You could do that.
Okay.
That's true. And re-injecting basically just means that we're providing another power source, that we're basically boosting power. Typically in DC, you can't re-boost the power. You can't change it again. It's just what it is. And typically what we'll see as we'll look through this in a little bit later is we have to keep in mind our length from our source to our string or to our load, and we have to adjust that basically on what we need to find from our voltage and our current levels to give us our proper power out there. This is an example, if you will. Hopefully this will shed a little better light on how to use this voltage drop formula. And it's not what we're really doing. We're trying to just figure out what our wire size is. What gauge wire are we going to use to connect from our power supply to our pixel string, right? Or to whatever LEDs or whatever lights we have. It could be incandescents for that matter. Okay, so this is our formula again right here for our wire size based on our voltage drop formula. So again, it's the 2. K is our constant. D is the distance from the power supply to the actual string or the load. That's the amount of current that we need to have utilized down there at that particular load. And this is our volts DC, and that would be the output of the supply. It could be 12, it could be 5, it could be 24, it doesn't matter. Still, we need to take that 3% of that. So looking at what we have here, this is the, if you will, the extrapolation of that. We're going to have 2 times 12.9, which doesn't change. 75 feet was our example here. It's going to take 1.5 amps. So we would put that, do all of our multiplication. We would then divide that by 12 volts DC times 0.303, which would give us that 0.36 that we saw before. Now, that number that we get by doing all that math gives us the circular mills. You'll notice that you've got 8,062.5. Kevin, can you turn me back on that? And you'll notice I've got number 10 gauge wire here. All right, 10 gauge wire. Whoops, get out of the way. There we go. So at 8,062, okay, 8,062, if you were looking for 8,062, you would not find it. What we have to do is we will take that number and we will find the closest one we have. That's not below it, but above it. So what we would see here, this guy right here is 8,234. We would need to go up to the next level because we fall in between this at 8,600 something what we had. To the next level of our normal wire size, which would be number 10. It's at 10,383 circular mills. So the way this chart works and the way that we work with that formula is we find that number of circular mills, we come to our chart, and we find the number that's going to be closest to it above that level. Or if you're right at it, of course that would be what you would use. And this is the wire number we want to use. We're not going to use circular mills, we're using circular mills to determine our wire size. So if we wanted to double check this, we can also use another part of this same formula, except now what we will actually be able to do is determine what the actual voltage drop will be based on a certain size wire. Okay, we found the wire size here using this one. If I want to figure out, okay, well, I know that I'm going to be 75 feet, I know that I'm going to have a 1.5 amps that I have to have down there. So if I try to figure out, well, if I put a number 10 wire on it, okay, you'd go to the chart, you'd go right back to the chart. Remember, that was 10,383 off the chart, and you'd plug that guy in right here. Circular mills, we use the wire size. By doing the math on this, we would come out with, it is going to give me a voltage reduction or a voltage drop of 0.279 volts. For that length of wire, okay, with that amount of amps flowing through it, and that diameter or that cross-sectional area of that wire. So what does it tell us? Well, 2.79, well, we remember that we don't want to exceed more than a 0.36 voltage drop. We're well within that. Okay, that's the maximum, 0.36. We're at 0.279, so we're well below our 3%. We're less than 3% variation, which means our circuit is going to be fairly effective at that point. So by using these guys right here, can you turn it back one more time, Kevin? If you use this formula here, find your wire size. If you're trying to figure out, well, I've got this conductor, I want to use it, will it work in the condition? Then you would use this voltage drop formula right here. That's the one we saw. That's this one right here. So this voltage drop one right here allows me to figure out what my actual voltage drop is based on the wire size. This one allows me to determine my wire size based on the voltage I need to provide to it, the current that needs to be there, and the distance. These numbers here are going to remain the same. So with these two in our arsenal, we can more or less figure out what our wire size would have to be based on these particular pieces of information. Hopefully that makes a little bit of sense. Okay. Here's a couple things to remember for us. First of all, your volts DC. Remember, volts DC is talking about two things. We're talking about voltage, and we're talking about direct current. All right? Current and voltage are not the same. Voltage is the pressure that pushes the electrons, which is the current through the circuit. That gives us watts. All right? So volts DC, two things we're looking at, cannot drop more than 3% of the required voltage. The required voltage is going to be what we call the nominal voltage or the design voltage. In our case, for my examples, was all 12 volts. You might be using 5-volt modules. Volts cannot be boosted. Okay, DC typically cannot be boosted or increased. It is what it is. Now, if you get to the other side, like Mark was talking about before, and you decide you're going to inject it again, it means we're just reapplying another source. Okay, to help fill in, if you will, those losses, if you will.
So Pete,
yep.
Just one more point there.
Yep.
So you can't basically, it can't be boosted, but if you have a power supply that can output more voltage, say you have a 5-volt power supply and you have a rheostat there, you can adjust it up to like 5.3 or 5.6 to help you with that voltage drop compensation.
Exactly right. Exactly right. That's another approach to what we're talking about here. So what basically Mark was just saying there is that you have a voltage supply. Okay, we have a power supply here. If we were looking at, so let's say for instance, we wanted to provide 12 volts, but our wire that we had in the run we were going to have is only going to allow us to get 11 volts down there. Okay, well that means is I've got to make up for that voltage drop by 1 volt plus I've got to take into consideration the 12 volts. So I need a 2 volt increase there. So what he was saying was what my case would be with, instead of having a 12 volt at this point, I would want something around a 14 volt power supply. And you really wouldn't have to have a rheostat there because the wire itself would provide the reduction of the voltage for you. Okay, by using our formula again, you could actually say to yourself, okay, it acts like a big resistor there, or in opposition to that current flow. And by doing so, I'm going to get the exact amount of voltage that I want down there at the end by using more voltage here. But if I was to take this though, there's a caution. If I was to take that 14 volt supply and take it down there and plug it onto the actual string, maybe you want to test something, maybe you're going to do some bench testing, you're going to overvolt, you're going to overpower that thing by that 2 volts, and that's significant. Okay, so we don't want to, if you're going to use these supplies and you're going to use larger voltages, then what you have to remember is you can't take that and apply it to that nominal or that 12 volt one. In my application we had 14 volts on the supply. You wouldn't want to put that on a 12 volt string. Okay? So we can't really increase it. There are ways we can kind of cheat around it, as we're kind of alluding to here. Primarily, if the DC is your voltage, your direct current voltage are too low, you're going to have to move. You typically are going to have to move your power supply closer to your load, or your load closer to the power supply. That's how you can compensate as well. We're kind of doing the same thing, except we're taking the resistive levels, if you will, the voltage levels that we are dropping, and shortening them or decreasing them by bringing that in a shorter period or shorter area. Increasing the wire size, as I said, does not increase voltage drop, or does not increase voltage DC here. It does not increase. What you have at the end of that line on DC is what you have. Okay, you can't transform it up. You can't make it happen differently. So keep in mind, volts DC is what it is. You cannot increase it. Watt's law, basically so we can understand Watt's law, we've looked at that a little bit there. We've been able to size our power supply using that. And we've also been able to figure out our loads based on that. Watt's law is very useful to us. Size your power supply 20% larger. This is a rule of thumb. This is a rule of thumb. If you feel that you want to make it 10%, that's up to you. 20% is my rule of thumb. 20% is what the National Electric Code allows us to put on total current draw for any circuit, no more than 80% of the full rated current value. So if I had a 20 amp circuit in my house, when I'm putting my loads on this and calculating those loads, I want to put no more than 16 amps of load on there. Or I basically only want to use 80% of my circuit. Why? For this very same reason. I don't want to overheat my conductors. I don't want to run my levels to the very top and wear things out, overheat them, and reduce the life expectancy. So basically, prevent overheating and to allow for ambient conditions. Ambient conditions are those that are temperature related, things that happen out in the field. Maybe we have some corrosion taking place out there that changes things for us. These are things that are around our displays, around our light sources, and around our power supply. So that 20% in there allows for that particular overcompensation, if you will. Voltage drop formulas, as we saw there, to size wire that we need for the required load. We can also figure out if we have proper wire size, maybe in our toolbox or maybe in our garage. We can also figure out if that wire size is going to work for what we want it to do. Okay. All right. And most important, have a very Merry Christmas. And yes, I know, it is May, but if you are like we are and you have CLAP, which is basically Christmas light addiction problems, it's Christmas every day. So take care all. I hope you have a great time. Merry Christmas.
Thanks, Pete.
Good job.